discuss. The first thing is k-nearest neighbor classifier, and the second is classification and regression trees. Very brief comments about these classification classifiers. So concerning k-nearest neighbors, this is a very simple technique, very simple. This technique is based on compactness and continuity hypothesis. And actually, I'm introducing these techniques here just for your just an overview of different possibilities, just for an overview of standard. Just for an overview of standard classifier and classification techniques, because this is the only, because you will need this for working, for solving your homework. So, compactness hypothesis is a rule, it means that similar objects belong to centers. So, if you have similar animals, like looking similar, then possibly these are the same type of an animal, right? Continuity hypothesis means that similar objects have similar characteristics, right? Well, also quite obvious assumption. Of course, it doesn't always happen. Moreover, for example, this hypothesis, it depends significantly on which characteristics you select to characterize an object. But if these hypotheses are true, then you can exploit these hypotheses in order to construct a very simple classifier. First of all, what are close objects? What are similar objects? We assume that two objects are similar if characteristics of these objects are similar. But in our case, usually the characteristics of objects are represented by some multidimensional vectors. And so similar characteristics means that the distance between the corresponding multidimensional vectors should be small. The standard way to define the distance is to use, for example, the Euclidean or weighted Euclidean distance, or for example, Manhattan distance, or any other distance. This is the case of multidimensional vectors. In case of well, of course, there are many situations when objects can be represented by some more complex data. For example, it can be strings, which is very relevant for biology. And the question is how to calculate the similarity or distance between two strings, especially in case of these two strings have different lengths. This is the same situation as in case of time series. What if you have two time series in different scales and of different lengths? Of course, if the time series are in the same scale and they have the same length, in this case you can use the Euclidean distance. In case the time series have different length, you can use so-called dynamic time warping. I don't want to go into detail now. Dynamic time warping means that you try to find the closest point for each point of one time series. You try to find the closest point of the other time series. And to do this, you can solve so-called quadratic optimization, dynamic optimization problem. It's not very difficult. There are computationally efficient algorithms for this, and this allows you defining distance between two time series of different lengths. Anyway, what I want to say is that there can be difficulties to define similarities or distances between objects represented by some data with complex structure, like time series or sequences of strings and so on. So this is it's not so easy thing to develop, to define. But if you have such thing, then you can say that these two objects are similar because their characteristics are similar, and these two objects are not similar because their characteristics are significantly different in terms of this similarity function. And the idea of the k-nearest classifier is very simple. You have a set of objects, x, y, y, I. And so what we do next? Okay, what is written here is quite complex. I will explain this in simple terms. So you have a set of objects. So this is your set of objects. Then you get some new observation. And for each of these objects, you know its label. So you get new observation. You calculate the distances from this observation to the k nearest neighbors. And this is why you need this distance function or similarity function. And then for each of these objects, you know its label. And then you see, and then you just evaluate what is the most frequent label among the k nearest neighbors. And this is exactly the prediction you make for this new object. That's it. Because this is the consequence of those two hypotheses. If your object is similar to some other objects and these some other objects have specific label, then there is high probability your new object has the same label. Quite obvious assumption. That's it. Here there are two main drawbacks. The first main drawback is that you have to keep the whole data set. So if your data set is big, it may cost some resources. The second drawback, so you need memory, you need to use some fast search algorithms. And the second drawback is that if objects have some complex description like strings or time series or whatever, progress for example, then it's not so easy to define a proper similarity function. Because accuracy of the classification will significantly depend on it. And of course, somehow you should also tune the number of k nearest neighbors. How many k nearest neighbors you should use? The answer is you should use cross-validation. And there is some example here in the slides. An obvious thing to use to select the number of k nearest neighbors is to use some hold out data set. So you extract some small part of your training data set. You construct a classifier, you estimate accuracy of the classifier on the validation data set, and then you see how this accuracy depends on the number of k nearest neighbors. And here is it for one of the standard classical, I would say, example. So you see that the optimal choice for the k nearest neighbors here is around 8. In practice, usually the number of k nearest neighbors is around just several. You just take 3 k nearest neighbors, 5 k nearest neighbors, not more. Too many k nearest neighbors is not good. Too small a number of k nearest neighbors. Too big number of k nearest neighbors is also not good. Well, that's it about KNN. Any questions?
Yes, I have. Can you clarify, for this type of classifier, should we store not the weights, but all the training?
Yes, you should store all the data.
Oh.
But nowadays, well, it's